Welcome to the Shape of Space Tensors, Multidimensional Arrays. This is the third in 3 lectures concerning tensors and related topics. The first lecture was on the Einstein notation, and the second lecture defined tensors in terms of multilinear maps. In this lesson, we're going to define tensors as a multidimensional array. This is the definition that's more commonly used in computer applications such as machine learning. I would recommend at least having a look at the first 2 videos before going to this one. As I mentioned on the previous slide, we have another way of defining a tensor in terms of a multi-dimensional array. I have a reference here to a Wikipedia article also on the same topic. A multi-dimensional array becomes a tensor when its components satisfy a consistent transformation law under the change of basis of the underlying vector space. And I mentioned this at the end of the previous lesson. So the point here is you can define a multi-dimensional array like a vector or a matrix or a 4-dimensional entity. But you need to have this additional property to be officially a tensor. Now in practice, when people use tensors in computer science like machine learning, they're mainly just interested in the multidimensional array, and they won't typically go the extra step to ensure the transformation law simply because it's not needed. But I just mentioned it here. It's multidimensional array plus the transformation law under change of basis that together give us an equivalent definition of tensor from the multilinear mapping that we saw in the previous lesson. Just as a vector in n-dimensional space is represented by a 1-dimensional array of n components relative to a chosen basis, a tensor of any order is represented by a multidimensional array with respect to a basis. For instance, a type 1,1 tensor is represented as a 2-dimensional n by n array with respect to a given basis. The numbers in the multidimensional array are known as the components of the tensor. Each component is labeled by a set of indices that indicate its position within the array. These indices are typically written as subscripts or superscripts following the symbolic name of the tensor. For example, the components of a second-order tensor T could be denoted Tij, and that's what we did in the previous lesson, where I and j are indices running from 1 to n, assuming our vector space is of dimension n, or alternately is t superscript I subscript j. Whether an index is displayed as a superscript or a subscript depends on the transformation properties, which I'll talk about in the following slides. While Tij or Tij written subscript superscript style can both be expressed as n by n matrices and may even share numerical values with respect to a fixed basis, they obey different transformation laws under a change of basis. As such, they represent different mathematical objects. Consequently, adding them together would be inappropriate despite superficial similarity of the array structure. So I'll talk more about this in the next few slides. So let's look a little bit deeper into this distinction between the Tij or Tij written this way here, subscript versus superscript. So a subscript index like I in Tij refers to a covariate index that transforms with the basis vectors. So if you remember from the previous lesson, these bottom indices refer to the vector space. A superscript index like I in Tij refers to the contravariate index. That's the dual of our vector space. It transforms with the dual basis. So if you write something like this here, the bottom refers to the vector space, and this refers to over which the tensor is defined, and the superscript refers to the dual of the vector space. Yeah, so as I mentioned here, T sub ij has two covariant indices, a tensor of type 2, 0, so two instances of the vector space and no instances of the dual. And then this here would represent one instance of the vector space and one instance of the dual in the mapping of the tensor does from the domain to the codomain, which is just the real numbers. So both can be represented by n grids of numbers in a given basis, but they live in different tensor spaces. Again, this is going back to some things we talked about towards the end of the previous lesson. So when you have just covariant indices like we have here, only involving the vector space itself, then this change of basis here involves a product of the change of basis from the vector space to the another basis for the vector space. When you have this type of index here, then you need to use the inverse of the change of basis matrix corresponding to the contravariant index, and then you use just the regular change of basis matrix for the covariant index, the vector space itself. So this illustrates why these behave differently, and you need to take that into account. And I'm just giving you one example. I mean, there's an infinite number of examples where you would have I, J, K, L, M, and maybe just one contravariant, or the opposite of that. We have a lot of contravariants and just one covariant. Okay, so this came out of, just to give credit, this right up here came out of a conversation with ChatGPT, which I believe is correct, and so with so few changes here and there, I reused that. On this slide and the next, I have a Python program that multiplies two 3 by 3 by 3 tensors, basically four-dimensional tensors. It makes use of the Python TensorFlow package. The operation for matrix multiplication is the @ sign. There's other ways of multiplying. I use this. This is the usual multiplication you use with 2 by 2 matrices. So let's just look through this quickly. I imported the TensorFlow as TF, so I can just use a shorthand for this package. And I believe you need to import install the package in your Python environment first, which I did. So here's our first tensor, and I'm just inputting it basically. So it's three matrices. This is one, this is a second, this is a third. That's why it's 3 by 3 by 3. So if I wanted to pinpoint, say, that element right here, this number 6, I would need three attributes. First, I would need to say which one of these three matrices, so it would be 3. And then within this matrix, I would need to point the second row, third column. That would give us the 6. So you need three attributes or three indices to pinpoint a particular element in a 3 by 3 by 3 tensor. Then the second tensor, I called it T2, and I inputted it the same way. It's pretty simple. And then I printed out the first tensor, and I just gave it a name here, and then the tensor itself. Then I print out the second tensor, and then I multiplied this times this. So the way it's done is you multiply this matrix times this matrix times this matrix times a third, and then you get another 3 by 3 by 3 tensor. So let's look at the results on the next slide. We have the output of our program here. This is just a printout of the tensor T1. You notice it's three matrices, and this is T2, and this is the product. It goes matrix by matrix, so it's this times this gives you this times this gives you this times this gives you this. For example, the 46 would be this row times this column. We would get 4 plus 32 is 36, and then plus 10 is 46. On this slide and the next few slides, I have some visualizations of tensors that I took from different papers in a book. So this first one is from this paper listed down here, and the authors show a zero-way tensor, a scalar, then a one-way tensor, which is a vector, and of course it doesn't have to be 3, it could be n. Same thing here, a two-way tensor is a matrix, it doesn't have to be 3 by 3, it could be 10 by 10 or some other, doesn't even need to be square. Then this is a three-way tensor, and we saw an example of that in the previous 2 slides on the Python program. Then if you take multiple of the three-way tensors, you get a four-way tensor and so on. This picture is from an online article. I gave the reference here. So you have a one-dimensional, he didn't bother to talk about the scalar, but you have the one-dimensional tensor, two-dimensional matrix, three-dimensional like our Python program. Then if you take a bunch of these, you have four-dimensional, so it's a collection of three-dimensional tensors. Then, as you guessed it, the five-dimensional tensor is a collection of so each, I guess he's going vertically, so each one of these is another four-dimensional tensor, which comprises 5. Then if you take these and you start lining them up, you have a six-dimensional tensor. So you get the idea. These can get bigger and more complex, and you need multiple indices to actually pinpoint a particular scalar element in something of this size here. This particular diagram comes from this book that I referenced here, and this little chart or axes, set of axes, I added to help explain things. This is only a three-way or third-order tensor, but the authors want to show different ways of viewing it. So in the first view, our tensor x, you notice they have a colon for the first index, and then j and k for the other two indices. So basically this is saying pick a j and k. So pick something here like 2, 3, and that would be one of these columns, and then you vary over the I. So you pick one of the columns and then you vary over the I. Then here you notice the middle index is free, and the other two are chosen. So you pick I and k, and then you vary along the j-axis here. So, for example, that one sticking out there could be one of the specified by this. Then the third option is you specify I and j, and then you let k vary, so you get these tubes going into the screen. Then you have 3 more options where you just fix one of the 3 indices. So for example, if you fix I, then you would fix a particular height, so to speak, and then j and k would vary, so that this is just giving you one of these planes. Or you can fix j and then let so fix one of the planes going this way into the screen, and then let I and k vary to get a particular location. Then you can do the same thing where you fix k, so the depth basically, and then I and j give you where you are on one of these planes. Okay, so that's yet another way of looking at a third order tensor, and it kind of goes back to what I was saying about needing multiple attributes to pick a particular point. Here it's just showing if you pick 2 attributes or 3 or 1 attribute, you can get either these different types of tubes, or what he's calling columns, rows, and tubes, or you can get sort of a planar slice. The total number of indices required to uniquely identify each component of a tensor is called the rank or order of a tensor, and we saw that in some of the examples in this lesson. This should not be confused with the dimension of the underlying vector space, which is for us normally the real numbers, so that's of dimension 1. A tensor of rank R can be viewed as an R-way array, which is why tensors are sometimes described as multidimensional arrays or multi-way arrays. Just as the components of a vector change under a change of basis in a vector space, the components of a tensor also transform according to a rule determined by the type of tensor. Each index in the tensor transforms independently, either covariantly or contravariantly. I'll explain this more in the next slide. To illustrate the point I made at the end of the last slide, consider a change of basis in the vector space V, where the new basis vectors, given by this symbol here, was E sub I and a hat, are expressed in terms of the old basis vectors E sub j as follows, using the Einstein summation notation. So the summation is over j. Here A, I, j are the entries in the change of basis matrix A, with the index j referring to the original basis and I to the new basis. This follows the covariant transformation law because the vectors are transformed by the change of basis matrix itself, A. For the dual space, V star, the basis vectors E superscript j transform with the inverse of matrix A, given by this here. The above formula follows the contravariant transformation law because the basis vectors transform by the inverse of the change of basis matrix, this here. More generally, the components of a tensor with multiple indices transform according to a combination of contravariant and covariant rules, one for each index. If an index transforms with the inverse of the change of basis matrix, as I said before, it is said to be contravariant and is written as a superscript. If it transforms with the matrix itself, the change of basis matrix, it is termed covariant and is written as a subscript. The main distinction between defining a tensor as a multilinear map, which we did in the last lesson, versus a multidimensional array, as we're doing in this lesson, lies in how the change of basis formula is treated. In the multilinear map definition, as we saw at the very end of the last lesson, the change of basis formula can be derived, whereas in the multidimensional array definition, it must be explicitly included as part of the definition. So we need to add that change of basis property that we saw at the end of the last lesson when we're defining a tensor as a multidimensional array. Now, in practice, and from what I've seen in machine learning and other computer applications, the interest is really in the multidimensional array aspect and much less so in the change of basis. So you may have a lot of applications where you really don't need to add this additional capability, this additional condition. The elements of a tensor transform in a specific manner when the basis changes, guaranteeing that the tensor itself remains unchanged, independent of coordinates. This transformation rule is what sets tensors apart from generic multidimensional arrays, which, as I just said, is sometimes all you may need. Not every array qualifies as a tensor because tensors must adhere to the precise change of basis rules. In the context of machine learning and numerical computing, the term tensor is often used informally to refer to multidimensional data structures that generalize scalars, vectors, and matrices. So this would be without the change of basis rule, as I mentioned in the previous slide. So we've already seen some diagrams earlier of this, but I'll mention it again here. So the vectors are one-dimensional arrays. Then you have matrices, two-dimensional arrays. I'll just give some examples here, used for representations like images, height and width, or weight matrices in neural networks. And then higher dimensional arrays, and we saw some diagrams of that earlier. For example, in mini batch RGB images, batch plus height, width, and channels, or input tensors and transformer models. However, these, referring to the examples I gave in the previous slide, are not tensors in the strict mathematical sense as defined in differential geometry or physics. In those fields, a tensor is not just a container for numbers, it is an object that follows specific transformation rules under changes of coordinate systems, change of basis. A true tensor's components must adhere in a precise way when the basis or reference frame changes, preserving its geometric or physical meaning. By contrast, in machine learning, for example, tensors are simply efficient numerical containers with no inherent transformation laws. They serve as a convenient way to store and manipulate multidimensional data, but they do not necessarily respect the rigorous mathematical properties of tensors in physics and differential geometry. And that's fine. Eventually you need, there's no reason to put additional conditions. This relaxed usage is practical for machine learning, where the focus is on computation rather than coordinate invariant properties. However, it is important to recognize the distinction when moving between fields like deep learning and theoretical physics. Okay, so that's the end of the 3-lesson series on the Einstein notation and tensors. And just a personal note, I've tried to learn about tensors several times in the past, and I've given up. It's a very impenetrable topic, and I think a lot of it has to do with there's different perspectives. If you look at a physics book, they'll look at it one way. If you look at a math book, typically differential geometry, they'll look at it another way. And if you look at a machine learning or computer computation type of book or paper, they'll look at it another way, and it's quite confusing. So hopefully I put together at least the different perspectives here in how the tensors are defined and how different aspects are needed for different applications.